Hi, we are Alejandro Perez, Eduardo Garza, David de la Garza, and today we're going to resolve the section 2, number 15. And for this problem, we have a variation of rules that we need to know to solve this. And these rules are the derivative of e to the u is, and when you have ax, it becomes ln to the a. So this is a problem that we got. And now my partner Alejandro is going to solve this problem for you.
Hello. At first you need to put the sign of integral in each part of the problem. And then to have a rule that secant squared to the u is equal tan to the u. So now we know that secant squared is equal as tan to the x minus the another rule, cosine to the u is the same as sin to the u. So we consider the 8 sin of x. Then for this part, for the derivative of x is 1, so it stays the same. And for the next one, we use this rule, and we got 4x over ln of 4 plus a. We will solve the section 1 problem that is asking the range of R of a projectile is, and they give you this formula, where the initial velocity in feet over second and the angle is the angle of elevation in radians. If the initial velocity is 2500 and the angle is changed from 10 to 11, then determine the change in the range of the projectile. The rule for getting change is delta change, that is y2 minus y1. We will use y2 as 11 and y1 as 10. So I will put the formula here.
So right now I am going to do number A, that we need to determine the change in the range of the projectile. So I am going to do all the work, and then I'm going to show off the paper and explain step by step. So I'm going to show a photo of the work so it can be seen clearly, but I'm just going to explain what I did. So I took the formula of the change in the range, that is 2500 squared divided by 32 sin times 2, and they gave us triangles that were 10 and 11. So what I did, I multiplied the angle times 2 and get the number in both angles. And then that I had all my information ready, what I did was subtract the final rate minus the initial rate, and then here it is. We have 2500 squared divided by 32 times sin of the final rate, that it is 0.38397, minus 2500 squared divided by 32 times sin of the initial rate, that it is 0.34907, and the answer is 6363.33. So now that we have our first problem resolved, we need to use differentials so we can approximate the change in the range of the projectile. So I'm going to start to work here, and then I'll show you all the process, right? So what I did in number B was to use differentials in the formula. So what I did was I keep the 2500 squared, but instead that it was over 32, it's over 16, and instead of sin, it's cosine, because it's a differential. So then you need to multiply the cosine with the sin of the angle that we were told, the initial angle, that is 10 times 2, and it was the number that we have in the last problem, and it's this one, 0.34907, and then you multiply it by the subtraction of angle 11 and angle 10, that it is angle 11, it is equal to 0.9199, and angle 10 is equal to 0.17453, and the answer it is 0.01746. So we multiply it all, and it gives us 6408, and it is more or less it's more or less as the same as the one that we used with the change of the range.
Okay, for questions C and D, I'm going to answer for you. I'm Eduardo Garza. The C questions: the results within the context of the situation. We answered that it infers on how the height of the projectile changes when the angle in radian changes. So when the angle in radian changes, it affected the height of the projectile. And on D, the question is, under what circumstances is it better to calculate the actual change, and when the approximate change? We answered on function to time referring in wind. If there is wind, we can imply it is an actual change, and if there is no wind, then it's an approximate result.